Hi student, in today's lecture again we will discuss the remaining part of isomerism, structural isomerism, and we have already discussed chain isomerism, positional isomerism, functional isomerism and metamerism. So in structural isomerism the remaining part is tautomerism. Tautomerism is a special type of functional group isomerism in which two functional group isomers are in dynamic equilibrium. This isomerism is due to the shifting of hydrogen atom between two polyvalent atoms. So one tautomer is converted to the another tautomer by shifting of hydrogen atom between two polyvalent atoms. For example, HCN. In this HCN, this hydrogen can shift between carbon and nitrogen. If hydrogen shifted to nitrogen, then a new structure is formed. These two remain in dynamic equilibrium. So this is the first type of tautomerism called as isocyano tautomerism. In second category, again, if this hydrogen atom shift between this carbon and oxygen, a new species is formed that will be in dynamic equilibrium with the parent species. So this is called as Keto Enol tautomerism. Keto Enol tautomerism. This is the keto form having ketonic functional group, and this is enolic form having enolic functional group. Similarly here, if this hydrogen can shift between carbon and nitrogen, new group is created. So this is called as nitro AC nitro tautomerism. And one more example. If this hydrogen atom shift between carbon and nitrogen, then a new group is created. So this is called as imine, enamine, tautomerism. Imine and enamine tautomerism. So basically tautomerism is a special type of functional group isomerism in which two functional group isomers are in dynamic equilibrium, and these functional group isomers which are in dynamic equilibrium are called as tautomers, and these tautomers are self-interconvertible. The interconversion is because of shifting of hydrogen atom between two polyvalent atoms. Like here, the hydrogen is shifting between carbon and nitrogen. Here also carbon and oxygen. Here between carbon and oxygen, and here between carbon and nitrogen. So this particular type of isomerism is called as tautomerism. Now, keto-enol isomerism is most important type of tautomerism. So further we will do keto-enol isomerism. In this type of tautomerism, keto-enol tautomerism or keto-enol isomerism, it is a type of tautomerism a type of tautomerism in which compound having keto group and enol group are in dynamic equilibrium. Keto group means compound having either aldehydic or ketonic type of functional group. So any compound having this type of structure or this type of structure in which there is carbon side chain with single bonded carbon, double bonded carbon, any type of carbon atom, ketonic type of carbon atom. Or in other words, we can say any compound having this type of structural formula where R is either hydrogen, any alkyl group or phenyl group. R is hydrogen, alkyl or phenyl are called as compound having keto group. And all these compounds can choose tautomerism, keto-enol isomerism. And this compound will be in dynamic equilibrium with enolic form. Now to draw this structure of enolic form, what we have to do, make a bond between hydrogen and oxygen and remove bond from carbon and hydrogen and make it between carbon and carbon. So this bond will shift between hydrogen and oxygen. This bond will cleave and will shift between carbon and carbon. So new compound form will have structure of this type. So here there is a carbon hydrogen bond has been cleaved. So a bond formed between carbon and carbon and oxygen and hydrogen, because hydrogen is shifting between carbon and oxygen. So this is the keto form. And this is enol form. So remember that any compound in which ketonic form is in dynamic equilibrium with enolic form is called as keto-enol isomerism. So any compound having this type of structure representation where R is either hydrogen or alkyl or phenyl. Remember that this carbon atom should be sp3 hybridized carbon atom. Let's say discuss conditions for keto-enol isomerism. Conditions for keto-enol isomerism. First is that all enols shows keto-enol isomerism. All enol shows keto-enol isomerism. All enols shows keto-enol isomerism. This is the first condition. Now, second condition, compound that satisfy following representation shows keto-enol isomerism, where this R should be hydrogen, any alkyl group, and phenyl group. So what is the requirement? Requirement is that there should be an aldehyde or ketonic type functional group. Aldehyde or ketonic type functional group. If R is hydrogen, then this will be aldehydic functional group. If R is alkyl and phenyl group, then this will be ketonic functional group. And from this aldehydic and ketonic functional group, there should be an sp3 hybridized carbon bonded from this ketonic or aldehydic functional group, an sp3 hybridized carbon, and from this sp3 hybridized carbon atom there should be hydrogen atom. So any compound having this type of structure can show tautomerism. For example, identify compounds that can show tautomerism or keto-enol isomerism. That can show keto-enol isomerism. First compound is CH3, C double bond OH. Second is CH2, CHOH. Third is PHCHO. Then PH, C double bond O, CH3. CH3 whole thrice, C, CHO. CH3, CH2, C double bond OH, CH2 double bond CH, C double bond OH, So these are some examples, and we have to identify compounds that can show keto-enol isomerism. So try them. Just take which among the following will choose. So I am giving you just 3 minutes. Okay. Now first of all, identify how many of the following are enol, because all enol shows keto-enol isomerism. And in enols, an OH group is bonded to double bonded carbon atom. Enols means to say any compound having a carbon-carbon double bond and OH group bonded to this carbon-carbon double bond are called as enols. So think this is an enol, so it shows tautomerism. It is an enol, so it shows tautomerism. This is also an enol, so it also shows tautomerism. In remaining, there is either an aldehyde functional group or ketonic functional group. So we have to check it whether there is a hydrogen atom bonded to sp3 hybridized alpha carbon atom. Alpha carbon atom means to say the carbon atom directly attached to the functional group. Carbon atom directly attached to the functional group is called as alpha carbon atom. So in this compound, this is the C double bond O of aldehyde type, and this is the alpha carbon atom sp3 hybridized, and there are 3 hydrogen atoms, so it also shows keto-enol isomerism. Now in this compound, pH means to say phenyl group, benzene ring. So benzene ring in bond line notation can be represented by this representation. And now, first of all, this carbon atom is alpha carbon atom and it is not sp3 hybridized, it is sp2 hybridized. First thing. Second, here there is no hydrogen atom. So we have to identify all these things in this order. First, there should be a CO group of aldehyde or ketone type. Second, there should be an sp3 hybridized alpha carbon atom. And third one, there should be a hydrogen bonded to this sp3 hybridized alpha carbon atom. So here alpha carbon atom, sp3 hybridized alpha carbon atom as well as hydrogen both are missing. So this compound can't show Tautomerism or keto-enol isomerism. In next compound, it is ketone type C double bond O, and this is again sp3 hybridized alpha carbon atom, and here there are 3 hydrogen atoms. So this compound satisfies all the conditions of keto-enol isomerism, so it shows keto-enol isomerism. Now in this compound, again, if we complete it by writing as complete structural formula, then you will notice that there is sp3 hybridized alpha carbon atom, but there are no hydrogen atoms bonded to this sp3 alpha carbon atom. So hydrogen is missing on this carbon atom. This hydrogen is missing. So this compound can't show keto-enol isomerism. Now in this compound, this is the aldehydic type CO group. When we take R as a hydrogen, this is the first thing. Second, this is the sp3 hybridized alpha carbon atom. And here there are 2 hydrogen atoms, so it shows keto-enol isomerism. It shows keto-enol isomerism. Now in this case, here there is an aldehydic type C double bond O, and this is the alpha carbon atom, but it is not sp3 hybridized, it is sp2 hybridized. It is sp2 hybridized. So this condition is missing, so it can't show keto-enol isomerism. Now in this compound, this is the C double bond O, and this is alpha hydrogen atom. So C double bond O, alpha hydrogen, alpha carbon atom, sp3 hybridized alpha carbon atom, and hydrogen bonded to this sp3 hybridized alpha carbon atom. So it shows keto-enol isomerism. Now in next compound, these alpha carbon atoms are not sp3 hybridized. All of them are sp2 hybridized. All of them are sp2 hybridized. So again, the condition of sp3 hybridized alpha carbon atom is not satisfied, so it can't show tautomerism or keto-enol isomerism. Now in this compound, this is the aldehydic or CO type ketonic type CO group. You can't consider this group as a aldehyde or ketone type CO group because on this side there is no R group. Because R can be either hydrogen or alkyl or phenyl. Here it is the ethoxy group. So you can't consider this group as a CO group because it should be CO of either aldehyde type or ketone type. And from this CO, these are the sp3 hydride alpha carbon atoms. And from these sp3 hydride alpha carbon atom, hydrogen atoms are bonded. So this compound shows keto-enol isomerism. So in this way, we can check whether a given compound can show keto-enol isomerism or not. Now, which form will dominate at equilibrium? Because keto form and enol form are in dynamic equilibrium. And percentage of these forms, that is keto form and enol form, are in percentage of keto form and enol form in this equilibrium depends on various factors. It depends on temperature, it depends on solvent, it depends on the substrate, that is the compound itself. It depends on the presence of some other acids and bases, etc. So it is very difficult to find out the structure of dominating form, whether the ketonic form will dominate or enolic form will dominate. But in general, it is observed that keto form is thermodynamically more stable than enol form. Hence, equilibrium remains shifted towards keto form because of more thermodynamic stability. Equilibrium remains shifted towards more stable form. So, suppose this is any compound that satisfies the condition of Tautomerism. So let's take them different type of groups, R double dash, R triple dash, or we can write them as a R1, R2, R3. Now when it is in dynamic equilibrium, then this equilibrium lies towards keto form. Now what do you mean by thermodynamic stability? Here we can place this one, because this is R dash, and this is R double dash. So this equilibrium remains shifted towards this form. This form is keto form, and this form is enol form. Now, thermodynamic stability means to say, in keto form, there is one CH bond and one carbon-carbon single bond and one carbon-oxygen double bond. In enolic form, there is a carbon-carbon double bond, at least carbon-oxygen single bond and oxygen-hydrogen single bond. The sum of bond dissociation energies of these three bonds is more than the sum of bond dissociation energy of these three bonds. Sum of bond dissociation enthalpy is more than the sum of dissociation enthalpy for these three bonds. So that's why ketonic form can exist at higher temperature because of its higher bond dissociation enthalpy, because of its higher decomposition temperature. It will get decomposed at higher temperature because of its high value of bond dissociation enthalpies. Well, we have taken here the minimum bonds. Any ketonic form will have at least these three types of bonds, and enolic form will also have these three types of bonds. So in most of the cases, keto form is thermodynamically more stable than enol form, hence equilibrium remains shifted towards the keto form. This equilibrium remains shifted towards the keto form. So percentage of ketonic form at equilibrium will be greater than that of enolic form. But it is also observed in few cases that percentage of enolic form becomes slightly greater or very high than that of enol form. The percentage of enol form become much more than that of keto form at equilibrium. In general, percentage of keto form will be more than that of enol form, but in some cases, percentage of enol form become more than that of keto form. Now, in these special cases, it is because of the presence of extra stabilizing factor. So remember that due to the presence of extra stabilizing factor, enol form may become more stable than keto form, and because of this extra stabilizing factor, this equilibrium may shift slightly or completely towards enolic form, and equilibrium may shift toward enolic form. Percentage of enolic form may become greater than that of keto form. Now these extra stabilizing factors are: number one, extended conjugation in enolic form, intramolecular hydrogen bonding in enolic form. Aromatic character in enolic form. Less steric hindrance in enolic form. Less steric hindrance in enolic form. So if any one of them is present in enolic form, then enolic form will be stabilized much more than that of keto form, and its percentage will become greater than that of keto form. So if we take some example, now this compound can show tautomerism, keto-enol isomerism, because this is the ketonic type CO group and this is sp3 hybridized alpha carbon atom having hydrogen atom. Conjugation means alternate arrangement of multiple bonds. Conjugation means alternate arrangement of multiple bonds. Carbon-carbon double bond, carbon-oxygen double bond, and carbon-carbon triple bond. So these double bonds are alternately arranged. So here there is a conjugation. Here there is also conjugation, and this conjugation is extended with carbon-oxygen double bond. But this carbon-oxygen double bond is not in extended conjugation with this benzene ring, because multiple bond of this benzene ring and multiple bond between C and O are not alternately placed. In between these two double bond, there is two single bond. So it can't make them alternate. When we read in arrangement, double bond, single bond, double bond, single bond, double bond, single bond, single bond, double bond. So it means these two are not in extended conjugation. This alternate arrangement is not extended in remaining part of the molecule. While in this case, the entire system is in extended conjugation. Double bond, single bond, double bond, single bond, double bond, single bond, double bond, single bond, double, single, double, single, double. So here there is extended conjugation. So enolic form of this compound comparatively more stable than that of keto form. Similarly, now in this compound, this hydrogen as well as this hydrogen can participate in keto-enol isomerism with this CO group. So let's say we are considering this hydrogen atom. Anyone can participate. This is the structure of enolic form of this compound. And in this structure, here there is a possibility of intramolecular hydrogen bonding. So this intramolecular hydrogen bonding is responsible for extra stability in enolic form. intramolecular hydrogen bonding. So enolic form become more stable than keto form. Aromatic character means presence of benzene ring or benzene type ring. Aromatic character means to say presence of benzene ring or benzene type ring. For example, benzene ring or benzene type ring means there should be a 6-member ring with 3 alternate multiple bonds. So here there is a 6-member ring, but there are no alternate multiple bonds. But during tautomerization, here there will be a benzene ring with alternate multiple bonds. So this is responsible for aromatic character. So due to the presence of benzene ring, the compound will be an aromatic compound, and aromatic compounds have extra stability because of them, because of resonance in these compounds. Aromatic compounds are resonance stabilized, and the extent of resonance stabilization is very high. So whenever there is a chance of presence of aromatic character, then that phenomena, then that process and that reaction will be highly stable, highly feasible process. Similarly, if we consider this compound, this compound also shows tautomerism, because instead of carbon, instead of sp3 hybridized carbon, here we have taken sp3 hybridized nitrogen atom. So during tautomerization, this structure will form, and here this structure is a benzene type ring, so it is aromatic. A benzene type ring is responsible for aromatic character. And less steric hindrance, suppose we have this compound, steric hindrance means crowding around an atom due to the presence of some bulkier groups. So this carbon atom is sp3 hybridized carbon atom as well as sterically hindered carbon atom. Sterically hindered carbon atom means to say it is surrounded by some bulkier, bigger size groups, because these angles around this carbon atom are 109.5 degree angles because of its sp3 hybridization state, and it can also tautomerize, and due to tautomerization, hybridization state of this carbon atom will change to sp2. Will change to sp2. So now angles will increase. This carbon atom is sp2 hybridized, and sp2 hybridization result in increase in angle. So this angle will become 120 degree. So this is less sterically hindered, while this is more sterically hindered compound. So steric hindrance means to say crowding around an atom. For example, this is carbon with 4 hydrogen atom, and this is carbon with 4 iodine atom. Now you can imagine size of iodine atom with respect to hydrogen atom. Now in these 4 compounds you can say this is the size of hydrogen atom, and this is the size of an atom of iodine with respect to hydrogen. So this carbon atom is a sterically hindered carbon atom due to the presence of these 4 bigger size iodine atoms. So large crowding is there around this carbon atom due to the presence of bulkier substituent, and these angles are 109.5 degree because of its sp3 hybridization state. Similarly, around this carbon atom there are 3 tertiary butyl groups, and tertiary butyl group is a very big substituent. It is a very big substituent. So this is the steric hindrance. So less steric hindrance in enolic form is responsible for more stability of enolic form. So it's all about tautomerism. Among structural isomerism, tautomerism is very important. So now I end my lecture here. You must revise it properly. Thank you.